In this presentation, I will be explaining about LC oscillators and crystal oscillators. Coming to LC oscillators, the feedback part there will be inductor and capacitors. Therefore, there are two types of LC oscillators that we are going to explain. One is Colpitts oscillators, Hartley oscillator and Colpitts oscillators both are LC oscillators. Now let us first see Colpitts oscillator. And this is a circuit diagram of a Colpitts oscillator in which you can see a transistor in common emitter configuration, and this is the biasing resistors, rotative biasing R1 and R2, and the is a RF choke in the collector, and the output of this one, here you are getting the output, oscillator output, and that is fed back to the input through a L and C, that is C1 and C2, their midpoint is grounded, and across that one an inductor L is connected. So this is the feedback path C1, C2, and L constitutes the feedback path, and that output is of the feedback is given to the input through a coupling capacitor. So this is a Colpitts oscillator circuit diagram in which the output frequency of oscillation, that is output is available at this point. The frequency oscillation of this output is given by 1 by 2 pi root of L into Ct. L into Ct means it is a total capacitance, which is actually it is the series capacitance of these two things. Therefore, C1 C2 divided by C1 plus C2. C1 C2 divided by C1 plus C2 is the total capacitance, and the output frequency of oscillation is of a Colpitts oscillator is given by 1 by 2 pi root of L into Ct. Therefore, at the output of transistor are two capacitors C1 C2, and that placed across a common inductor, that is inductor L, and the center of these two capacitors are grounded. The center of the sum that is being grounded, and the output frequency 1 by 2 pi root of L into Ct. Now we have to derive the equation for this output frequency equal to 1 by 2 pi root of L into Ct. Slide we are going to derive the equation for the output frequency of oscillation of a Colpitts oscillator, and Colpitts oscillator f equal 1 by 2 pi root of L into Ct. We are going to derive the equation for this one, and in order to derive that one, I am going to consider a generalized block diagram of a LC oscillator circuit, like LC oscillator circuit. In that one, here the transistor is replaced by its HIE is the input impedance, and the HF into IB is the current source. Therefore, this is a P, C, and emitter. This is a transistor. This one constitutes the transistor, and the output of the transistor through the feedback path you are considering is the impedance Z1, Z2, and here we will be getting it is equal to ZA, ZB, ZC. One is ZA, other one is ZB, and that is center is grounded, and across that Z1 and ZA and ZB you are connecting another impedance ZC. The same thing in another method it is redrawn, this one, in which this portion represents the transistor equivalent circuit, and these are the feedback path ZA, ZB, and ZC. In this type of generalized block diagram representation, under sustained oscillation, to have a sustained oscillation, the condition for to get sustained oscillation is, as per the Barkhousens criteria, the product of gain of the amplifier and the feedback factor A into beta, that should be equal to unity 1. For that condition, I am not going to derive that condition equation. At least you take care that take this equation as such. It is to get A beta equal to 1. The condition in this is that HIE into ZA plus ZB plus ZC, that is ZA plus ZB plus ZC is added, that is multiplied with HIE, plus ZA into ZB into 1 plus HFE, plus ZA into ZC, that is ZA into ZC, that should be equal to 0. For you just take this equation like, when not to get A beta equal to 1, this should be equal to 0. Now we are going to apply in this case Colpitts oscillator, what is ZA, what is ZB, and what is ZC. As per this equation, this is the condition to get a sustained oscillation A beta equal to 1. Now look into the Colpitts oscillator. What is ZA? ZA is given by the impedance due to the capacitor C1, or that is equal to 1 by j omega C1. or that can be multiplying j numerator and denominator, you can get minus j omega c1. Similarly, what is ZB? ZB equal to 1 by j omega c2 or minus j omega c2. Similarly, what is ZC? ZC is coming across that one. In this one, that is across that inductor, which is equal to impedance is given by omega into L. That is j omega L. That is ZC equal to j omega L. For Colpitts oscillator, we have seen what is ZA, what is ZB, and what is ZC, and we are going to substitute these values of ZA, ZB, and ZC in this equation like HIE into ZA plus ZB plus ZC into that plus ZA, ZB into 1 plus HFE plus ZA, ZC equal to 0. Then you are going to derive the condition for the to get what should be the output frequency of this Colpitts oscillator. Continuing the derivation of output frequency of a Colpitts oscillator, in which we have derived a condition to get A beta equal to unity, and in that one we found out what is ZA and what is ZB and what is ZC. Now we are going to substitute these values of ZA, ZB and ZC in that equation, that is HIE into here ZA plus ZB plus ZC, and here here ZA, ZB into 1 plus HFE, and here we can get it is equal to 1 by omega, that is ZA into ZC, that is equated to 0. Or we are going to substitute in these values of ZA, ZB and ZC in that equations, and as per this equation we are expanding that one, and then you will be getting it is equal to minus JHIE into 1 by omega C1. JHIE is taken outside, 1 by omega C1 plus 1 by omega C2 minus omega L minus then 1 plus HFE divided by omega square C1 C2 plus here we can get cancelling this one, L by C1, that equals 0. So this is the condition to be satisfied to get a beta equal to 1 or to get a sustained oscillation. Now from this equation you have to equate when imaginary part equal to 0, that is then you getting the condition, the output frequency, what should be that. Then you have to equate the real part is also equal to 0, then you will be getting the condition to get sustained oscillation. So for considering this equation, considering the imaginary side equal to 0, that is equating the imaginary part of the equation to 0, this is the imaginary part, minus JHIE into this one is the imaginary part. Therefore that is equal to 0 means that 1 by omega C1 plus 1 by omega C2 minus omega L should be equal to 1 by omega C1 plus 1 by omega C2 minus omega L should be equal to 0. Then only the imaginary side will become equal to 0. Or we can get it as 1 by omega C1 plus 1 by omega C2 equal to omega L. Or omega taking to the side, we get 1 by C1 plus 1 by C2 equal to omega square L. Or omega square is given by 1 by L times 1 by C1 plus 1 by C2 if you C1 plus C2 divided by C1 C2. Or here 1 by L into C1 plus C2 divided by C1 C2. This is omega square. Omega square. For omega equal to 2 pi f. Substituting for that for omega, we will be getting the frequency of oscillation is f is given by 1 by 2 pi into root of C1 plus C2 divided by C1 C2 into L. Or here this can be written as 1 by CT equal to, that is the series combination of C1 and C2. C1 C2 divided by C1 plus C2 can be replaced by CT. Therefore here it will be getting 1 by 2 pi root of 1 by CT into L, or 1 by 2 pi root of 1 by L into CT. Therefore the frequency of oscillation is given by, for a Colpitts oscillator, the output frequency of oscillation is given by 1 by 2 pi into root of inductors L into CT, or total capacitance, which is equal to C1 C2 divided by C1 plus C2. Therefore this is the output frequency of a Colpitts oscillator equation. Equating the imaginary part of that one equal to 0, you found out what is the frequency of oscillation, f equal to 1 by 2 pi root of L into CT, where CT is the C1 C2 divided by C1 plus C2. Now the condition to get to this oscillation is that can be obtained by equating the real part of that equation equal to 0. Real part is given by 1 plus HFE divided by omega square C1 C2 plus L by C1. That should be equal to 0. This is the real part that is made equal to 0, or here 1 plus HFE divided by omega C1 C2 equal to L by C1, or 1 plus HFE equal to omega square C1 C2 L divided by C1, or C1 gets cancelled, or omega square L into C2. Therefore, the equation is that 1 plus HFE equal to omega square L into C2, where then omega square is given by, already we have derived the equation for omega square equal to 1 by L into C1 plus C2 divided by C1 plus C1 C2. It's already derived in the last slide. Therefore, here substituting for this omega square here in this equation, we'll be getting 1 plus HFE equal to, omega is replaced by this 1 by L into C1 plus C2 divided by C1 C2 into L into C2, or here C2 gets cancelled, or we'll be getting L and L gets cancelled, or we'll be getting C1 plus C2 divided by C1, or C1 plus C2 divided by C1 is equal to C1 1 plus C2 by C1, 1 plus C2 by C1. Therefore, 1 plus HFE equal to 1 plus C2 by C1 means that HFE should be equal to C2 by C1. Therefore, the condition to get sustained oscillation is that the HFE should be equal to the current gain in common emitter configuration. HFE should be equal to C2 by C1. This is the condition to be satisfied for the sustained oscillation in a Colpitts oscillator, and the output frequency can be obtained by equating the imaginary part of that equation. It is equal to 1 by 2 pi root of L into CT, CT equals C1 C2 divided by C1 plus C2, and this is the condition to be satisfied. HFE should be equal to C2 by C1. Second type of oscillator is Hartley oscillator. LC oscillator is Hartley oscillator, and Hartley oscillator is similar to the Colpitts oscillator with minor modification. And instead of using a tapped capacitors, previously we are using capacitors C1 C2, instead of that one we are using two inductors L1 and L2, and they are placed across a common capacitor. Here L1 and L2, and he has placed a common capacitor that is fed back to the input. Only thing, this output side feeding back circuit, there's a change from L1, L2 and C. Previously it was C1, C2 and L. So that is a change in a Hartley's oscillator in circuit wise, and that is fed back to the input. And this is again a transistor. R1, R2 is the biasing resistance, and RF is a choke in collector circuit. This is emitter biasing resistance, sorry, and C is the bypass capacitor, emitter bypass capacitor. See, therefore this is a common emitter amplifier. Output is given, and this is fed back through a feedback network L1, L2 and C. Now the output frequency in a Hartley oscillator is given by 1 by 2 pi root of C into LT. It is 1 by 2 pi root of C into LT. LT means total inductance. That is, when they are connected in series, it is equal to L1 plus L2 plus twice the mutual inductance. L1 plus L2 plus 2M is the total inductance. Therefore, 1 by 2 pi root of C into LT is the output frequency of oscillation that is available at this point. Or M is the mutual inductance between this inductance L1 and L2. Therefore, this is the circuit diagram of a Hartley oscillator, and this is the output frequency is given by 2 pi root of C into 2 pi root of C into LT. So this is actually used for a high frequency generation of a output frequency. In this one, to derive the output frequency equation for a Hartley oscillator, F equal to 1 by 2 pi root of C into LT, and again you have to take the generalized equation like to get A beta equal to 1. That equation you have to take, in which ZA is defined as here equal to J omega L1, and ZB is defined as J omega L2, and of course J omega L2, and J omega L1 plus J omega M is also coming. So mutual inductance is there, and B is equal to J omega L2 plus J omega M. Also mutual inductance also there, and ZC is given by 1 by J omega C, or equal to minus J by omega C. So this is a set A, set B and set C. These values are to be substituted in the previous equation what I already discussed, that is HI into set A plus set B plus set C plus set A set B into 1 plus HFE plus set A into set C. That should be equated to the 0, and substituting these values of the set A, set B and set C here, and then you are to equate to that equal to 0. Therefore, finally you are substituting these values here and you are equating to 0. Then here you will be getting an equation clubbing all those imaginary terms as well as the real terms here. You will be getting an equation relating this the inductance values and of course the frequency x omega etc. that will be mutual inductance etc. You will be getting an equation that contains the imaginary part plus the real part. Now to get the frequency of oscillation, normally we will be equating the imaginary part equal to 0 because total phase shift should be equal to 360 degree. Therefore, the imaginary side should be equal to 0. For equating the imaginary side of this equation, imaginary part of this equation to 0, you will be getting what is that here imaginary means this one, that is omega HIE into L1 plus L2 plus 2m minus 1 by here omega square C, that should be equal to 0. Or we can get L1 plus L2 plus 2m minus 1 by omega square C, that should be equal to 0. This is a condition for getting a sustained dose. In this case, that is, the frequency is being decided by this equation, equating the imaginary side equal to 0. And from this equation, you can get it as omega square C equal to, you have to take this side, omega square C, C equal to 1 by L1 plus L2 plus 2m, 1 by L. Or we can get omega square equal to, that is omega square equal to 2 pi f whole square, 2 pi f whole square into C into 1 by this one. Or can say frequency of oscillation f is equal to 1 by 2 pi into root of L1 plus L2 plus 2m into C. Or this L1 plus L2 plus 2m, that is called the total inductance. L1 plus L2 plus 2m is LT. Therefore, 1 by 2 pi root of LT into C. That is the frequency of oscillation. Therefore, output frequency of oscillation of a Hartley oscillator is given by 1 by 2 pi square root of LT into C, where T total inductance is given by L1 plus L2 plus 2m. L1 plus L2 plus 2m. That is the total inductance, and this is the frequency of oscillation of a Hartley oscillator. So the frequency of oscillation for a Hartley oscillator is equal to 1 by 2 pi root of LT into C, where LT equal to L1 plus L2 plus 2m. Now to get the condition for getting this oscillation can be obtained by equating the real part of this equation is equal to 0. Equating the real part equal to 0, L1 plus m into 1 plus HFP minus 1 by omega square C, that is equated to 0. Or from this equation 1 plus HFP equal 1 by omega square C into here it is equal to L1 plus m, or omega square omega square C is equal to omega square C equal to it is equal to 1 by L1 plus L2 plus 2m. L1 plus L2 plus 2m. That is already we derived that equation. Substituting for that omega square C here, we will be getting 1 plus HFP equal to L1 plus L2 plus 2m divided by L1 plus m. This is L1 plus m. And here L1 plus L2 plus 2m I can write as L1 plus m plus L2 plus m divided by L1 plus m. Or here it is equal to 1 plus L2 plus m divided by L1 plus m. Or that's equal to 1 plus L2 plus m divided by L1 plus m. That is equal to 1 plus HFE. Or HFE should be equal to L2 plus m divided by L1 plus m. Suppose the condition for get sustained oscillation can be obtained by equating the real part equal to 0. That you will be getting the HFE of this transistor, that should be equal to L2 plus m divided by L1 plus m, where m is the mutual inductance between these coils L1 and L2. Therefore, the output frequency equal to 1 by 2 pi root of LT into C, where LT equal to L1 plus L2 plus 2m. And the condition to get the sustained oscillation is that HFE should be equal to L2 plus m divided by L1 plus m. This is for a Hartley oscillator to produce a high frequency output signal. Next, we'll see that crystal oscillators. Previously, we have seen LC oscillators. Now, in crystal oscillator, piezoelectric crystal is used certain crystalline materials like rochelle salt, quartz crystal, etc. that can be used for crystal oscillators to produce oscillating frequencies. Therefore, that exhibits this material that is, that material exhibits piezoelectric effect. Piezoelectric effect means that when we apply an AC voltage across them, they vibrate at a frequency of the applied voltage. That is, when we are applying a voltage, when we are applying, we apply an AC voltage across them, that will be producing a mechanical movement or vibrations, which is at a particular frequency of the, the frequency of the applied voltage, and that is piezoelectric effect. Now, just reverse of that one, if you are conversely, when they are compressed or placed under mechanical strain to vibrate, then they will be producing an AC voltage. That's opposite to that one. If you make a vibrating mechanical movement, then it will be producing AC output voltage. Therefore, such crystals which exhibits the piezoelectric effects are called piezoelectric crystals. Piezoelectric examples, as we have seen, it is equal to the quartz crystal, rochelle salt, etc. These are examples of piezoelectric crystals. Therefore, the working of a quartz crystal here, a piezoelectric material, is the contactors are there. When the crystal is not vibrating, it is equivalent to a capacitor Cm. That is, it is as if a capacitor, when it is crystal can be considered as a equivalent circuit, can be considered as a capacitor Cm. It has two metal plates separated by a dielectric, and this capacitance is called the mounting capacitance Cm. So this can be considered as a quartz crystal, in which can be considered as a mounting capacitor Cm, in which two plates in between that it is insulatory. This is equivalent circuit of a crystal when it is not vibrating. Under not vibration case, this is the equivalent circuit with a Cm as the capacitance, that is the capacitance between the plate. This is the capacitance of the circuit. Continuing the crystal oscillators, when the crystal vibrates, it is equivalent to RLC series circuit. Therefore, the equivalent circuit of a vibrating crystal is an RLC series circuit shunted by a mounting capacitor Cm. Therefore, if it is not vibrating, it is simply Cm. And when it is vibrating, it can be considered as an RLC series. Therefore, the equivalent circuit of a crystal which is in vibrating condition, it is RLC series. Across that one, this mounting capacitance Cm is thus. Therefore, this is the equivalent circuit. When the crystal is vibrating, L is the electrical equivalent of the crystal mass, and C is the electrical equivalent of elasticity, and R is the electrical equivalent circuit of the mechanical friction. That is equivalent circuit. This RLC is equivalent, and this friction equivalent, and the mass equivalent, as well as C is the electrical. C is the electrical equivalent of elasticity. That is RLC. That is coming in series. Therefore, the typical value of a 4 megahertz crystals are these values of R are L equal to 100 millihenry, and C equal to 0.15 picofarad, and R equal to 100, and Cm equal to 5 picofarad. And in that case, the Q factor is given by 1 by R into root of L by C, or that is a Q factor will be very large, like 26,000 is the Q factor of this oscillator, and the Q factor of a crystal is very high, that leads to high frequency stability. As the Q factor is high, the frequency stability is more. Therefore, this is having a very large Q factor, that indicates that it has a frequency stability is very large in the case of a crystal oscillator. Therefore, this is the equivalent circuit of a crystal when it is vibrating. When the crystal is vibrating, its electrical equivalent circuit is, as already explained, a RLC in series, Cm in parallel. Capacitance value of the Cm and C are relatively low. Example 1 picofarad, and C is 4 to 40 picofarad for Cm, and this is equal to for C. At low frequencies, the impedance of the crystal is controlled by extremely high value of Xm, Xcm, and this XC. At low frequencies, the impedance of the network is high and it is capacitive. At low frequency, it is capacitive. Therefore, as frequency is increased, RLC branch approaches its resonant frequency. At some definite frequency, we'll be getting that XC will be equal to the capacitive reactance will be equal to the inductive reactance. That we call it as resonant frequency. At resonant frequency, this reactance gets cancelled and you will be getting maximum, that is resonant condition current or minimum impedance, resistance impedance. At series resonant frequency, impedance that is becomes purely resistive. XC and XL gets cancelled at resonant frequency. Therefore, the series resonant frequency is given by series equal to 1 by 2 pi root of LC, where L and C here. Series resistance equal to 1 by 2 pi root of LC hertz, where L is in Henry and C is in farad. Therefore, this is the diagram showing the frequency range as well as the reactance of that one. At here capacitive and here inductive, and at in this point it is purely resistive. That is the resonant frequency happening here. At a particular frequency, you are getting the minimum impedance, that is resistance. When XC and XL are equal, that gets cancelled. To the frequency response of the crystal oscillator, in that one frequency versus, of course, the reactance. If you see that one, if less than the resonant frequency equal 1 by 2 pi root of LC, it is capacitive, and if it is more than the resonant frequency, it will be inductive. Inductance reactance will be more than the capacitive reactance, and this is the inductive region. Therefore, at slightly higher frequencies, the net reactance RLC branch becomes inductive, and crystal now acts as a parallel resonance circuit. And for this reason, the crystal offers as a high impedance in the case of a parallel resonance circuit, and the frequency at which the vibrating crystal behaves as a parallel resonance circuit is called the parallel resonant frequency. That is, at particular frequency, it is behaving as a parallel resonance circuit in which this will be coming in parallel, and that corresponding equation for the parallel resonance is given by 1 by 2 pi root of L into CT. 1 by here the series here series resonance 1 by 2 pi root of LC, and this is equal to 1 by parallel resonance equal to 1 by 2 pi root of L into CT, and CT is given by the parallel, the C and that one, that is here C into Cm divided by C plus Cm, that is the total capacitance CT, and this is the parallel frequency, that so parallel resonant frequency FP is coming this one, and where here CT is less than C, then here IP is always FP is always greater than Fs. That is here. That is why always the parallel resonant frequency FP will be always more than the series resonant frequency Fs. Fs is this one, and parallel resonance is this one. Therefore, the corresponding here we can see that one. This is the resonant frequency, series resonant frequency, and this is the parallel resonance frequency. In parallel resonant frequency, it is highly reactance will be the inductive, and in this case here it is in this one the series resonance resistance will be minimum. Therefore, this is called the series resonance frequency Fs, and this is the parallel resonance frequency Fp. Transistor crystal oscillator. In transistor crystal oscillator, this is a Colpitts oscillator modified to act as a crystal oscillator, modified act as a crystal oscillator. In that one, rather than connecting an inductor, this crystal oscillator is connected here, and the crystal is connected in the feedback circuit, and at parallel resonance of the crystal, the impedance of the crystal is maximum. Impedance is maximum in parallel resonance, and impedance is minimum series resonance, and the maximum voltage across the C1, allowing the maximum energy transfer through the feedback network. That is at maximum at the parallel resonance, its maximum energy is transferred this one, and feedback is positive, and a phase shift of 180 degrees is produced by the 180 degree shift is produced by this one, and it's again 180 degree phase shift is produced by this one. Further, a phase shift of 180 degrees produced by the capacitor, capacitor voltage divider circuit. By this one, it is producing a 180-degree phase shift, and so that total phase shift is equal to 360-degree. Or the oscillator oscillates only at this frequency FP, and it is very much stable. And this has the high order of frequency stability, and quality factor of the crystal is also very high. For frequency stability is very large in the case of a transistor crystal oscillator, in which it is similar to the Colpit oscillator. Only thing is that inductor is replaced by the crystal, that is quartz crystal is, and that is fed back to this one. Therefore, this is be producing a very highly stable output frequency that is decided by it is parallel frequency resonant frequency. Let us see a problem on the crystal oscillator. Problem is AC equivalent circuit of a crystal has the following values: inductance 1 Henry, capacitance 0.01 picofarad, R equal to 1000 ohms, and Cm, that is equal to 20 picofarad. Calculate the series and parallel resonant frequencies Fs and Fp. And solution: L is given, C is given, and Cm is given, and R is given. Series resonance frequency equal to 1 by 2 pi root of Lc. 1 by 2 pi root of Lc. 1 by 2 pi into square root of L is given as 1 Henry, and similarly C is given as 0.01 picofarad. You will be getting 1589 kilohertz. That is the series resonance. And Fp is given by parallel resonance 1 by 2 pi root of L into Ct, where Ct is the parallel combination of, not parallel combination, it's actually series resonance, series combination, because two capacitors, when they are connected in series, you will be getting C into Cm divided by C plus Cm. That is total capacitance you will be getting. And substituting that one here, you will be getting it is equal to 1.5. Here we can see that one, the Fp is almost equal to Fs. That is, if the crystal is used as an oscillator, the frequency of oscillation will lie between 1.5, because almost between this one. This is a parallel resonant frequency 1590, and series it is equal to 1589. In between it is, that is why it is a very stable one. The frequency of oscillation will be like between 1589 kilohertz and 1590 kilohertz. That is, frequency of oscillation of a crystal oscillator is very much stable. That is clear from this frequency values like Fs and Fp.